Okay, for chapter 26, 1 through 3, for our class activities, we're going to do concept questions 1 through 9. Okay, now again, just to remind you that you should study these sections in detail and understand the main concepts there so that you can use these as applications of those concepts and fortifying those concepts. So go ahead and look at concept question 1. Try to answer that question on your own and then come back here. Okay, so the electric field over some space, electric field in the x direction is constant. Okay, it's constant. We're given values. Okay, so this is in volts per meter, but it's at a constant 100 volts per meter. And the question is, draw the potential versus position graph if we know that the potential at x equals 0 is 0. So what is the main idea that relates the electric field to the potential? How do we find potential from the electric field? So remembering that the potential difference is equal to the negative of the integral of Ex dx, where this was E dot ds, and then I took the dot product to take just the component of the electric field in the direction of the motion. Since we're looking along the x direction, our motion is along the x direction, and that's why this is plotted as Ex. If this was Ey, this would mean nothing. Okay. All right, so using that, we know that this right here is the same thing graphically as the area under a curve. And so the minus sign means I just need to flip that. So positive area means a negative change in value. Okay, so since we know we're starting at 0 and we have a positive area here, my graph would be more conveniently written this way. I'm starting at 0 and I'm going to end up with a negative change in values. So here's my x in meters, here's 1, here's 2. Okay. And so after 1 meter, the area here is 100 times 1, or 100 volts. 100 volts per meter times 1 meter gives me 100 volts. So I get 100 volts right there. And I go another length, and I go another meter, I gain another 100 volts. And so I end up with, those are negative, I end up with a straight line with a slope of 100 volts per meter, which is correct because going backwards, the electric field is the slope of a potential versus position graph, only the negative of it. So this is a negative 100 volts per meter, giving me a positive 100 volts per meter for my value here. Okay, now the next problem, number 2, is like this, only in reverse. So try and apply the same ideas to number 2. Okay, in this case, our potential graph is constant at 100 volts over 2 meters. Okay, and so what does the electric field graph look like? What's the main idea? Okay, if potential difference is equal to the area underneath an electric field curve, well, we can reverse that. Is that the electric field in the x direction, since we're going in the x direction, is the negative of the slope. Negative of the slope of a potential versus position graph. And what's the slope here? It is 0. So our graph of electric field versus position is just 0 for all. The slope is a constant 0. So again, our main idea is that potential is the area underneath the curve for of an electric field curve, or electric field is the slope of a potential line curve. Okay, let's do 3 now. Go ahead and take a look at 3. See if you can apply, this is our kind of main idea, these 2 ideas, this is really where it came from. Let's apply these ideas to number 3. Okay, so if the electric field is 0 everywhere, what can you say about the potential everywhere. Could you say that the potential is 0 in that region? If the electric field is 0 everywhere within a region, then is the potential 0 or the potential difference? You can see it's the potential difference is 0. So that means delta V equals 0, which could be for V equals 0 everywhere. That's a delta V of 0, or just V is constant, whatever it is. Okay, so 0 electric field everywhere simply means the potential is constant, kind of like what we saw with a conductor in electrostatic equilibrium. All right, so that's as much as we could say of this. All right, B says if the potential is 0 throughout a region of space, can you conclude that the electric field is 0? Okay. If V is 0 everywhere, then the change in V is 0. And if that's 0, then the electric field must be 0. Okay, because I can take steps. I can move a meter. I can move throughout this space. But the electric field must be 0 because the change of potential is 0 because the potential is 0. So yes, we can conclude that E equals 0 everywhere for this one. Okay, very good. Let's move on to 4. I'm going to draw this out, but you go look at the problem and try and solve it first. Okay. So here are equipotential lines. That line is all at 0 volts. That line's all at 10, and so on and so forth. And these lines are spaced equally 1 meter apart. We're shown a dot right here at 0.5 meter, and a dot right here at 3.5 meters. This is dot 1. This is dot 2. The question is, given that potential distribution in this space, what are the electric fields of vectors in their direction and their magnitude? Could you draw those vectors, and how big would they be? Okay, so what's the main idea to connect these two? We know that electric field is equal to the difference in voltage over the difference in space. And we learned earlier that electric fields point perpendicular to equipotential lines. And we learned that they point towards lower potential. So I know my vectors need to point this way. So let's assume that that one is that far. How big is it? Okay, we'll call that E1 in size. So we've already got the direction, so I don't need to put a minus sign. But it's the change in potential over the change in distance. Okay, now when you're thinking about that, if I were to try to find the slope of this point right here, well, what I do is I span it a little bit. I look a little bit up and a little bit down and find the rise over the run around that point. Okay, it's not good to do, if I'm trying to find that point, go from here to here, because if this is curving and I go from here to here, that's a very different value than if I go from here to here. And so the idea is for something that's curving, you want to get as close to it on either side. And so here, though you can get the same answer because things are constant, if I go from this side to this side of that dot, I'm going to get the most qualitatively correct answer. Well, and quantitative, but conceptually correct answer. So my delta V over my delta S is going to be 10 minus 1 over 1 minus 0. That's spanning my point, and I get 10 volts per meter, which I kind of could have seen. It's 10 volts every meter. All right, and then again pointing towards lower potential. So what's the value here then? What is the direction and size of the electric field at that point? So it's the same thing. It's pointing towards lower potential, perpendicular to the field line or the potential lines, and E2 is going to be 40 minus 30 over 4 minus 3, which gives me 10 volts per meter. So it's the same thing. All right, so again, see how we're using these ideas to solve these. All right, now go on and look at number 5. I'm going to draw it out, but you go try and solve it. Okay, so we have point 1 and point 2. So we're going to apply the same idea to this problem. If you do, to be careful, we want to go to either side of that spot. Now, things are changing here. They're not the same anymore. We don't have enough information in between 0 and 2 meters to know the details in here. So we can just assume we go from this spot to this spot, even though it's probably not going to be exactly right because this is off from the middle of that. But we can say for 1 that E1 is going to be equal to 10 minus 0 over 2 minus 0, and that's going to give us a 5 volts per meter. And it's pointing towards lower potential. What about E2? So to follow the same process, I'm going to go to either side of it. So I can go 40 minus 20 divided by 4 minus 3. Okay? And that's going to give me 20 over 1, or 20 volts per meter. Now, I could have gotten the same answer if I did 30 minus 20 over 3.5 minus 3. I would have gotten the same answer. But again, it's really important to be more careful with what we're doing, why we're doing a delta V. It's the same thing as a derivative, and so we have to be careful when things are changing. Okay, very good. Now let's move on to 6 and apply this. Okay, I'm going to draw it out, but you go try and solve it. And this is volts. All right, so this is my potential versus position graph, V versus X. And I'm told that at a location of 2 meters, I place an electron. Okay, what direction will it move? What direction will it move? Okay, or does it move, I should say. It does move, but how do we know what direction? How are you going to solve this? We have a potential versus position graph, and we ultimately want to say the electron's going to move. How do we figure that out? Okay, there's a couple ways we could approach that. We could use some of these ideas, because I know electrons, so if the electric field is pointing this way at a point, I know an electron would move opposite that. Okay, because electrons go towards positive charges, and electric fields emanate from positive charges. So I could tell what direction the electron would go if I know what direction the electric field is at these points. And so I could try and draw the electric field at these points, or draw an electric field curve. Now, I could do that a little more quickly to answer this problem and just use the idea that electric fields point towards lower potential. So if I'm at 2 meters, the potential is 0. Okay, if I go to smaller positions, so less than 2, the potential gets more negative or lower. Okay? And that means the electric field is going to point towards lower potential. And I could draw that all the way down here. At this point right here, the electric field would be 0 because it's the lowest point. Okay? Over here, the electric field is going to point this way because it's going to go towards lower potential. Okay, so all points along here. And this would be, so those would be my electric field vectors all the way along this. And so at that point, the electric field's pointing towards lower X, lower position, and therefore my electron should move to the right towards positive X. So Vx would be greater than 0. That's one way you can do it. Another way is to think about potential energy. Remember that potential energy is QV, and we have an electron that's negative EV. And so our potential energy curve will be scaled by the charge of an electron, but we could basically say it's going to be the inverse of this. And so if I draw that out, you're going to get something like, here's at that 2, this would be the potential energy of that electron, and a electron released from that point would want to go towards lower potential energy. Okay, and so we see that the electron would go this way again because it would get lower potential energy, and that's the same answer we got before. So we can either use our relationship between potential and electric field, or between potential and potential energy. Okay, go ahead and move on to number 7. Okay, with number 7, we have these field lines. These electric fields are constant and pointing like this. These are all electric field lines. And we have these just dotted lines for reference. They're not something physical there. I'm not saying it's an equipotential line or anything. These are just dotted lines for reference. And I've got points A, B, C, D, E, and F. Okay, we'll just call this line 1 and this line 2. So there's a couple questions with this. One, is the electric potential at point A higher, equal to, or lower than the potential at B? So what's the potential difference between these, or which one of these is at higher potential, or are they at the same potential? What's the main idea? Okay, so we know a few rules about electric fields and potential lines. One is that electric fields point perpendicular to surfaces of equal potential, and they always point towards lower potential, which means from here to here, the electric field is pointing that way, so B must be at a lower potential. Okay, and in fact, we could say that this line right here, since it's perpendicular to all these fields, must be some equipotential line. Okay, it's some constant value. So if it's 0 volts here, it's 0 volts here and 0 volts here because it's perpendicular to those electric field lines. Okay, now we can't say it about this line because this line is not perpendicular to those. I could say that B has the same potential as it does here, or as points here and here, and D has the same potential along of this line here, and F has the same potential along that line. But between B, D, and F, what I can say is that D is at a lower potential than B because it's further along. Okay, F is at a lower potential than B because it's further along from these perpendicular lines. So I can actually answer the other two questions in a similar manner. Go ahead and try and answer parts B and C with these ideas. Okay, so part C we did answer. This is an equipotential surface, and this one is not, okay, because it's not perpendicular. But what we can now do is we can say that the distance between this, since potential difference for constant electric field is ES delta S, that means potential difference, this is a smaller distance, this is bigger and even bigger. It means that the potential difference between E and F is greater than the potential difference between C and D, and that's greater than the potential difference between A and B. All right. Okay. So now move on to number 8. Okay, we saw an electroscope in class. Here's this electroscope, and it's got a metal leaf, and right now there's negative charges everywhere on it. The question is this metal leaf that's kind of sticking out because of the repulsion force between these like charges, is that at a higher potential, lower potential, or the same potential as the rest of this? How do we find that out? This is a conductor. This is all metal. That's why the electrons can move freely throughout it, and they've reached some stable state. which means this is a conductor in electrostatic equilibrium, which means the electric field inside equals 0 everywhere, which means that the potential difference is 0 everywhere, which means V is constant everywhere. So it doesn't matter if this is a thin wire, if it's in contact and electrons can move through it, then it's at the same potential once this has reached equilibrium, which is really fast. Okay, so this piece of leaf, this metal leaf that's sticking out, is at the same potential as the ball. Okay, last problem, 9. That's going to build off this idea and make it a little more quantitative. So go and look at exercise 9. I'll draw it, but you go look and try and solve it first. Okay, so if you're back, let's guide through this problem. This is the original setup. This is a charged sphere, conducting sphere. There's a conducting wire and a small neutral sphere. And then we connect them together. So we connect this together, so now it's connected. And the question is, rank the potential on 1 versus the potential on 2, the charge on 1 versus the charge on 2, and the electric field at the surface of 1 to the electric field at the surface of the other. So the potential, how does V1 and V2 compare? These are conductors that are connected via conducting wire, which means the whole thing is a conductor in electrostatic equilibrium. And if that's true, then the potential is equal. The potential is equal. All right, now that arms us with a way of comparing the charges on each. Now, I like to answer this one even without these new ideas of potential, is knowing that electrons are trying to get as far away from each other as they can. Where are they going to be? Okay? If we put more charge on here than on here, then they'd be awfully crammed, and they wouldn't like that. So there's got to be more charge in here because there's more surface area for them to spread out on. And so these electrons want to have about the same distance between themselves. And so there's got to be more charge on here. So we could have answered that just that way. But let's answer it with potential. Okay, you read in the text that the potential at the surface, or the potential from a sphere, a charged sphere, is equal to K, the charge on the sphere, divided by the distance from the center of the sphere, which, if we're going to talk about the potential right at the surface, because it's the same along the surface as well as inside, let's just plug in R1 as the distance from the center. So we're going to look at right here. Okay, well, KQ2 over R2, if I already know that these quantities are equal, then what does it say about Q1 and Q2? If R1 is bigger than R2, then Q1 should be bigger than Q2. So we can say Q1 is bigger than Q2, which is what we concluded earlier from a more fundamental idea. Lastly, the electric field. Okay, now we're talking about the electric field at the surface, not inside, because we know inside it's 0, but at the surface it's non-zero and points perpendicularly away. So that's the field we're looking for. So how do those fields compare? The field at R1, or the field for ball 1 versus the field for ball 2. Okay, so with this one, we know from Coulomb's law that the electric field for a sphere is equal to K Q1 over the distance squared. Now, if we're looking at just at the surface, that distance is just this R1, but it's squared. Okay. Now, if I compare this to this, that's the same thing as the potential over R1. If this is the potential, and it's only over one factor of r, and this is over two factors, then I just need to divide the potential by another factor of r. And that's our clue here. Now I can say we got V1 over R1 and V2 over R2. Okay, if the potentials are the same, so again, this is the electric field of 1, this is the electric field of 2 by this relationship. The potentials are the same and R1 is bigger than R2. That means the electric field 1 must be smaller than the electric field from 2. And that actually allows us to conclude something again, or another thing, is that electric fields are really big on sharply curved surfaces. Okay, so this small ball has a really sharp curve. It changes direction fast. A big ball has a small curvature. It's got a bigger radius, but that means a smaller curvature. It doesn't curve as fast, and this curves really fast. Okay, so the head of a pin is a super big curvature because on one side it's going up and the other side is going down. So a pin, that right there, has a huge curvature because it's going this way and then this way really quick. Okay, and so we can conclude from what we just saw here that assuming things are at constant potential is that pointed objects have really high potentials, and that's actually how we can utilize that, or really high electric fields. So like lightning rods, the goal of a lightning rod is to try and create a big electric field to drain charges fast from the air, and so they're really sharply pointed, and they can suck the charges out of the air and try and keep lightning from striking in the area. And if lightning does strike, it will want to go to that point. And so we can conclude that from here. Okay, well, that is the end of our class activity for today.